Welcome to the deep dive. It's the year 2026, and honestly, if you've been paying even a tiny bit of attention to the tech world lately, you have probably noticed a pretty massive shift in the vocabulary everyone is using.
Oh, absolutely. It's everywhere.
Right. Suddenly, every single AI breakthrough, whether we are looking at some mind-bending new robotics or artificial intelligence that can generate entire interactive movies from scratch, it's all being slapped with the exact same buzzword.
Everything is suddenly a world model.
Exactly, a world model.
It really has taken over the entire industry narrative. I mean, if an AI touches the physical world in any capacity or simulates a physical space, someone out there is aggressively branding it as a world model.
Which is exactly why we are here with you today. We are pulling from a singular, incredibly dense, and frankly, brilliant source for this one. It's a highly detailed video essay titled Comprehensive Analysis of World Models from the tech channel Silicon Valley 101.
A fantastic breakdown, by the way.
Truly. So our mission for this deep dive is to cut right through all this massive industry hype. We want to figure out what a world model actually is fundamentally, why the absolute legends of the AI field are currently betting everything they have on it, and ultimately,
And this is the big one.
yep, explore if this is the final missing puzzle piece to artificial general intelligence or AGI.
The claims surrounding this technology are bold, no doubt about it. But as we dive into the architecture today, I think we'll see that the enthusiasm isn't entirely without merit.
No, not at all.
Because the shift we're talking about here is foundational to how machines actually comprehend reality.
Okay, let's unpack this. And I have to say, I love the vintage library backdrop you have set up for your video feed today.
Vampy.
The dimly lit stacks of cognitive science textbooks and those old anatomical charts, it feels incredibly appropriate for where the story of this technology actually begins.
I thought setting the mood was fitting, because what's fascinating here is that world models are not some brand new invention cooked up by Silicon Valley developers just last week.
Right.
The underlying concept is actually older than artificial intelligence itself. It originates deeply within cognitive science. If we rewind all the way back to 1943.
Wow, 1943.
Yeah, a scientist named Kenneth Craik wrote a foundational book called The Nature of Explanation. And Craik proposed that humans don't just react to the world blindly or purely on reflex.
We're not just input-output machines.
Exactly. Instead, our brains are constantly building, refining, and updating these small-scale models of reality inside our heads. We use these internal models to simulate potential outcomes before we ever take a physical action.
So it's essentially that little voice or visualization in your head going, hey, if I push this heavy glass of water too close to the edge of the table,
It's going to tip over.
right, it's going to fall and shatter all over the floor. You don't have to actually push the glass to know it happens. You ran a physics simulation in your mental model.
That is the perfect everyday example. And in the AI world, researchers have been chasing this exact cognitive capability for decades. Back in 1991, Richard Sutton proposed something called the DINA architecture, which argued that an AI agent needs to learn a working model of its environment at the exact same time it learns how to act within it. But the modern framework we're really exploring today was formalized much later.
In 2018, right.
Yes, it was crystallized in a pivotal 2018 paper simply titled World Models, co-authored by David Ha and AI pioneer Jürgen Schmidhuber.
The brilliance of that 2018 paper is how it takes this incredibly massive abstract concept and breaks it down into three distinct manageable modules.
Vision, memory, and control.
Yes, vision, memory, and control. To really make this concrete for everyone listening, let me see if I have this framework right, using a physical scenario. Let's imagine you're a complete novice trying to play ping pong for the first time.
Okay, I like where this is going.
First, there's vision, or the V module. When that ball comes flying across the table at you, your brain is not processing every single pixel of the room.
Definitely not. You'd be overwhelmed.
It ignores the color of the walls, the pattern on your opponent's shirt, or the lighting fixture above. It compresses the scene and extracts just the essential vector information, the trajectory, the spin, and the speed of the ping pong ball.
And that compression is the critical part of the vision module. It takes millions of irrelevant data points from the environment and boils them down into a tiny mathematically manageable code that the brain can actually work with in real time.
Which sets the stage perfectly for the second part, memory, the M module.
Mm-hmm.
Think of this as your brain's internal physics engine, operating almost in a high-speed dream state. Before you even begin to swing your paddle, your memory module is rapidly predicting multiple futures.
It's running the simulations.
Right. It calculates, if I swing at this downward angle, the ball goes straight into the net. If I swing higher with more force, it goes out of bounds over the table.
Right. Predicting the immediate future based on all the physics data you've absorbed over your entire life.
Exactly. And finally, there is control, the C module. After your brain simulates hundreds of these possible swings in a fraction of a second inside your internal model, your control module steps in and executes the single best physical scenario in reality.
The ping pong analogy maps beautifully to the Ha and Schmidhuber architecture. Synthesizing their work, we can define a true AI world model as possessing three absolute core traits.
Okay, let's hear them.
First is representation. The AI needs to know what things are, where they are located, and how they relate to one another spatially.
Second,
Second is prediction. It must be able to simulate the future state of the world based on potential actions. And third is planning and control, knowing exactly what sequence of actions to take to achieve a desired outcome based on those internal predictions.
well, put simply, a world model is a compressed parallel universe running constantly inside the AI's architecture.
That's a great way to phrase it.
But wait, I have to play devil's advocate here because I know what you listening are probably thinking right now.
Oh, I think I know what you're going to ask.
For the past few years, the entire tech industry has been utterly obsessed with scaling up large language models. We have watched LLMs conquer complex coding tasks, pass logic tests, and ace medical and law exams.
They seem incredibly intelligent.
Yeah, so why is the industry suddenly acting like LLMs are not enough? Why the sudden, desperate pivot to world models?
To understand why the field is pivoting, we have to look closely at Moravec's paradox.
Moravec's paradox.
Right. It's a famous observation in robotics and AI research, which states that high-level reasoning like playing grandmaster chess, solving calculus, or passing a bar exam actually requires very little computational power for an AI.
Which feels completely backward to how humans work.
It does. For a machine, logic is relatively easy. But the basic instinctual skills of a one-year-old human or even a simple animal, things like visual perception, navigating physical space, or recognizing spatial relationships, those are incredibly difficult to reverse engineer.
It is genuinely wild to think that an AI finds quantum physics significantly easier than figuring out how to pick up a delicate coffee mug without crushing it.
It really is.
And the critiques of LLMs from the pioneers in the field are getting incredibly harsh in the source material. The video highlights Yann LeCun, who controversially argues that LLMs are basically a dead end for achieving true artificial general intelligence.
He does not hold back.
No, he points out that LLMs just learn the statistical correlations of text. They have zero direct tactile understanding of the physical world. He even goes so far as to predict that LLMs, at least as the primary driver of AI advancement, will be obsolete in 5 years.
Fei-Fei Li, another absolute titan of artificial intelligence, echoes the sentiment in the source. She describes LLMs with a rather poetic critique, calling them wordsmiths in the dark.
Wordsmiths in the dark. I love that phrasing.
It's very accurate. They are incredibly eloquent and persuasive, but they are completely disconnected from physical reality. The issue is their foundational diet. They use text tokens to understand the world, rather than the pixels of a 2D image or the 3D voxels. Yes, which are essentially 3D pixels that make up physical volume in spatial space. Because they lack that spatial data, their understanding is entirely hollow.
Let me test a scenario to validate that disconnect. If I ask a standard LLM, will a glass cup fall off a table if I push it? The AI will confidently answer yes.
Of course it will.
But it is only saying yes because it has ingested billions of documents where the text tokens for push, cup, fall, and table are statistically linked together, right?
Precisely.
It doesn't actually possess a mathematical intuition of gravity. A world model, on the other hand, actively simulates the physical mass of the cup, the friction of the table, and the force of the push.
The distinction is crucial. An LLM has the vocabulary of physics without the physical intuition. This is why world models and LLMs are not competitors. They are complementary.
They work together.
Exactly. The Silicon Valley 101 essay notes that world models will likely act as a sort of supersized GPT. The language model acts as the reasoning brain, while the world model provides the body, spatial perception, and physical intuition.
This brings us to how the industry is actually trying to build these parallel universes. Bridging the gap from text to physical reality is causing massive confusion, which is why the source outlines a really helpful 3-layer industry framework to categorize everything.
The framework clarifies the chaos beautifully. Layer 1 is the paradigm layer. This covers the abstract theories and mathematical rules of prediction we just discussed.
Right.
Layer 2 is the generation layer, which dictates how the AI actually visually constructs and represents this internal world. And Layer 3 is the purpose layer, which focuses on how we train AI agents to actually take action and survive within that generated space.
And layer 2, that generation layer, is where the absolute industry war is happening right now. And I see your background just flip to that glowing, rotating 3D wireframe matrix of a city.
I thought it was time for a change of scenery.
It is the perfect visual for the battle, currently splitting the tech world into two fiercely opposed paths: video generation versus 3D spatial generation.
The divide between these two approaches will likely determine the future architecture of AGI.
Let's start with Path A, video generation. We're talking about highly publicized models like OpenAI's Sora or Google's Genie 3. And here's where it gets really interesting. These models attempt to learn the laws of physics implicitly, simply by watching massive, astronomical amounts of internet video.
Just endless streams of data.
They ingest millions of hours of objects falling, cars driving, and waves crashing. The results are undeniable. Google's Project Genie 3 actually allows users to type a single text prompt, and it will generate a fully interactive, playable 60-second video game at 24 frames per second.
It's unbelievable to watch.
You can use a controller to run around and interact with a world that the AI is hallucinating frame by frame on the fly.
The visual output is genuinely stunning, but the Silicon Valley 101 analysis points out a fundamental limitation with Path A. Video generation is essentially just a skin, just a surface layer.
Exactly. If you pause a video model like Sora and ask for the precise mathematical dimensions of a car it just generated, it has absolutely no idea. It only knows how to arrange 2D pixels on a screen to create the optical illusion of a car. It fundamentally lacks an understanding of underlying 3D geometry.
Which opens the door for Path B, 3D spatial generation. This is the computationally heavy approach championed by Fei-Fei Li's new startup, World Labs.
A very different philosophy.
Very. Instead of generating a flat video that looks pretty, World Labs, which just hit a staggering $5 billion valuation, by the way, generates explicit mathematical 3D structures. If this model generates that same car, it knows precisely that the chassis is 4.5 meters long, 1.8 meters wide, and has a specific mass. It understands true spatial logic, how objects physically collide, and crucially, it knows what the hidden backside of the car looks like even if the camera angle cannot see it.
That level of spatial object permanence is incredible for robotics, but Path B suffers from its own severe bottlenecks.
What's holding them back? Generating explicit 3D geometry requires astronomical amounts of compute power compared to rendering a 2D frame. More importantly, they face a severe data drought.
Right. Because we don't have infinite 3D models lying around.
Exactly. The internet is an endless goldmine of 2D YouTube videos for Path A to train on, but high-quality, mathematically accurate 3D scans of the real world are rare, proprietary, and incredibly expensive to capture.
So the industry is locked in this race between the beautiful, data-rich illusion of video and the computationally exhausting but physically accurate truth of 3D spatial generation.
Yes.
But just generating a world layer 2 is only half the battle. The AI actually has to learn how to exist and act within it, bringing us to layer 3, the purpose layer.
Google is taking a highly pragmatic approach to the purpose layer with a project called Sima 2. They operate on the premise that gaming is the ultimate training gym for artificial intelligence.
Gaming as a gym.
Right. They are dropping AI agents directly into those generated game environments, but not just to beat a high score. Sima 2 uses these games to learn absolute physics constraints. By interacting with a digital environment, the AI learns that wood burns, water flows, gravity pulls objects downward, and solid objects cannot pass through one another.
So it's building common sense.
Exactly. The goal is that when this digital AI is eventually transferred into a real-world warehouse robot, it already inherently understands that a heavy steel box cannot float, and a glass pane will shatter if dropped.
That strategy makes total sense. You absolutely do not want a prototype robot practicing how to pour coffee in your actual physical kitchen and smashing 1,000 ceramic mugs in the process.
Let it smash digital mugs in a simulation first.
Exactly. But contrast that with Meta, and specifically Yann LeCun's radically different approach to taking action known as Dojepa. Dojepa looks at this entire generation battle between video and 3D and essentially asks, why are we bothering to render complex graphics at all?
If we connect this to the bigger picture, Dojepa is a masterclass in ruthless computational efficiency.
How so?
We can use a ball analogy to illustrate the difference. If you push a ball across a hardwood floor, A video generation model consumes massive amounts of computing power, trying to render the exact pixel-perfect shadows, the lighting reflections on the floorboards, and the texture of the ball in the very next frame.
It is wasting energy trying to make a cinematic movie of the event.
Precisely the issue. JPA, however, does not care about the lighting, the shadows, or the textures. It only calculates the abstract, hidden structure of reality.
Just the math.
Yes. Which way is the ball rolling? What is its velocity? Is there a solid wall in its path? Furthermore, if that ball rolls behind a couch, a video model struggles because the pixels disappear. JPA maintains object permanence. It tracks the abstract vector of the ball and knows it still exists behind the couch and will emerge on the other side.
That's brilliant.
By stripping away all the visual noise and focusing purely on causal structure, it is computationally lightweight. Knowing what will happen without needing to see it perfectly rendered is exactly the kind of abstract reasoning a physical robot needs to navigate a messy living room.
So what does this all mean for you listening to this today? Why does the architecture of JPA or SIMA 2 matter to your everyday life? Let's bring this right down to the tangible impact, because the successful deployment of world models is going to change almost everything about how we interact with technology.
The real-world applications are vast.
First, robotics. As we discussed, right now, if you change the lighting in a room or move a chair 2 inches to the left, a typical household robot gets confused and completely breaks down. World models solve this fragility. Robots will soon be able to practice a task entirely in their internal simulation and achieve what is called zero-shot transfer.
Meaning they don't need real-world practice?
Right. This means a robot can successfully perform a complex physical task in your real-world home on its very first try, having already simulated the physics of the movement 10,000 times internally.
The transportation sector will see an equally massive leap, specifically in self-driving technology. Companies like Waymo are utilizing world models to push past basic obstacle perception and move toward verifiable Level 5 autonomous safety.
Complete autonomy.
Yes. Instead of merely reacting when a pedestrian unexpectedly steps off a curb, the vehicle's world model will mentally simulate dozens of different branching futures in real time. It will predict the pedestrian's likely momentum, the friction of the wet road, and the behavior of surrounding cars, preemptively selecting the absolute safest route before the hazard even fully materializes.
And think about the wearables market. Those augmented reality smart glasses you might purchase won't just record video or show you text messages anymore. They will become a true digital partner.
Because they finally understand your environment.
Because they will have a world model running continuously. They will actually comprehend the 3D spatial layout of your house. They could actively warn you that the tile floor you are about to step on has water on it and is dangerously slippery. Or, while you are cooking, they can notice you're missing a crucial ingredient on a counter and alert you before you even turn on the stove.
It changes everything.
And for entertainment, we can forget about static, pre-programmed video games entirely. Entire gaming ecosystems, the micro-weather patterns, the global economy, the deep psychological personalities of the non-player characters will generate, interact, and evolve dynamically on the fly, customized entirely to your actions.
The societal benefits and conveniences are undeniably staggering, but the source material is very clear that we cannot ignore the dark side of this technological leap. This raises an important question about the physical risks we're inviting into our world.
Yeah, we have to talk about the risks.
Currently, if a large language model hallucinates, it might write a nonsensical poem or confidently invent a fake historical fact. It is annoying and perhaps a misinformation risk, but the failure is contained entirely to text on a screen. But we have to consider what happens when a world model hallucinates a fundamental rule of physics.
That scenario is genuinely terrifying. The Silicon Valley 101 essay refers to this specific danger as the sim-to-real gap.
The sim-to-real gap is where digital errors become physical casualties. Imagine a 2-ton autonomous heavy industrial robot operating in a busy warehouse, entirely guided by its internal world model.
Okay.
If that model suffers a systemic hallucination, perhaps it incorrectly predicts the friction coefficient of a concrete floor, or overestimates the structural integrity of a massive steel beam it is carrying. The AI is not just giving a wrong answer on a monitor. The robot will confidently execute a catastrophic physical maneuver, potentially destroying infrastructure or endangering human workers.
Because it thinks it's making the right move.
Exactly. A hallucination in a world model translates directly to physical danger in the real world.
Adding to that physical danger is the broader societal threat of reality blurring and the sheer monopolization of power. Building these high-precision predictive engines requires so much financial capital, proprietary data, and massive compute power that the barrier to entry is astronomically high.
It's not something a small startup can just spin up in a garage.
Not at all. The source warns we are looking at a near future where only a tiny handful of megacorporations possess the infrastructure to perfectly simulate reality. When you combine that monopolized power with hyper-realistic video generation, the potential for undetectable deepfakes, large-scale societal manipulation, and a complete loss of shared objective truth becomes a very immediate threat. If the digital simulation is mathematically perfect, how do you as a citizen know what is actually real?
It is a profound philosophical and societal challenge. As the video essay concludes, we are officially moving away from an era where AI is just a passive digital observer that predicts the next likely word in a sentence.
What's tipping off the screen?
AI is now rapidly becoming an active participant that comprehensively understands physical reality, predicts the future consequences of complex actions, and acts upon them autonomously. This transition from generating words to simulating worlds is the true, definitive turning point toward artificial general intelligence.
It really is the ultimate bridge from the digital void into our physical reality. And as we wrap up this deep dive into the architecture of tomorrow, I want to leave you with one final provocative thought to mull over today.
I think we need one after all of this.
We have spent this time talking about how these AI agents use world models as a digital gym, a safe sandbox to practice interacting with our reality. But think about the long-term trajectory of this technology. If these world models eventually become sophisticated enough to perfectly simulate not just physics, but the global economics, the political movements, and the complex social behaviors of our entire planet.
The entire system.
Right. At what point does the AI stop merely predicting our world and start quietly steering it from inside its own simulation? Are we simply building a highly capable tool to help ourselves? Or are we actively constructing our replacement's training gym?
Exploring the boundary between simulation and manipulation is exactly the conversation we need to be having right now before the generated world becomes entirely indistinguishable from our own.
Thank you so much for joining us on this deep dive. Keep observing the shifts in the technology around you. Keep questioning the reality of the media you consume, and we will see you next time.